Yeah, I think we can start now.
Yes, please. Mahalakshmi, go ahead.
Okay. Good afternoon, everyone. I'm Mahalakshmi. I'm privileged to be the host of today's event. It's my immense pleasure to warmly welcome all of you to this talk. This event is organized by Kareli, a math club of MTTS alumni, in collaboration with MTTS Trust. This is the first invited talk of 2025, and our speaker for today's talk is Dr. Argha Ghosh. Dr. Argha Ghosh is currently working in Manipal Institute of Technology, Manipal, as an assistant professor. His sequences, summability of series, and general topology. A heartfelt welcome to you, sir.
Thank you, Mahalakshmi. And thank you, MTTS, for giving me this opportunity. I think, shall I share the screen? Shall I go ahead, Mahalakshmi?
Sir, I have some instructions to say. Could you please wait?
Okay, please.
Okay.
Yeah.
So I have some important instructions to the audience. Feel free to ask any questions you may have, but please wait for unmute yourself until you are invited to do so. To ask a question, kindly use the raise hand feature in Zoom. For those watching on YouTube, please post your questions in the chat box. We will make sure they reach the speaker. Your questions are highly valued and will enhance our collective understanding of this fascinating subject. Over to you, sir.
Yeah. Thank you, Mahalakshmi. You are too formal. Yeah. Most of the time, tell you that don't be that much. Okay, let's. Okay. Is it all right? Visible?
Yes, sir.
Yeah, perfect.
But thank you, but I need to do not do this type of stuff. Can you stop others to, not allow, don't allow others to write on my screen?
Yeah, sure, sir. Yeah.
That's okay, but oh, it's gone. This is okay. Okay, I will start with a very simple definition. I think all of you know that. Let's suppose we have two metric spaces, xj and y rho, and we have a function f, and we call it continuous at p if either of the following conditions hold. So first is that whenever xn is a sequence converges to p, then if we take the sequence f of xn in y, then f of xn should converge to f of p. So this is first condition. Another condition is epsilon delta definition. For all epsilon greater than 0, there exists a delta. So this delta depends on the choice of epsilon and also the point p, such that distance between p and x is less than delta, implies distance between f of p and f of x is less than epsilon. Okay, so now we'll say that the function is continuous on x if it is continuous at each point of x. It's gone. Is it visible or it's gone? Slide. Is it visible to others? Mahalakshmi, is it visible?
No, sir. It is not visible.
It's not visible. Okay. Not working. Something wrong. Is it visible now?
Yeah.
Yes, yes.
Yeah. So now we have the definition of uniform continuous function. For each epsilon greater than 0, there exists delta. Now this delta depends on size of epsilon, but not of the points. So now whatever points x to y, x and w we have in x, then the distance between x, w less than delta implies that distance between f of x and f of w less than epsilon. So of course that if a function is uniformly continuous, it will be continuous at each point of x. So therefore f will be continuous on whole of x. Okay, so now there is one important thing to understand. That we know that if a function, if we go to the previous definition, if a function is a convergent, then convergence preserves under continuous function. But we also know that if a sequence is convergent to a point, then it is a Cauchy sequence. So now the question is, suppose we have a continuous function. So does it converge, preserve Cauchiness? That means if we have a Cauchy sequence, so if is a continuous function from x to y, and xn is Cauchy, can we always say that f of xn will is Cauchy in y? The answer is no. We know that we have a function if we take x as open 0 infinity and define our function f of x equals to 1 by x. So usual topology on x, then we have a function. We have with f of x equals to 1 by x is a continuous function, continuous on x, and we have a Cauchy sequence xn equals to 1 by n, and f of x of n will be equal to n. So therefore, this is and f of x of n is not a Cauchy. So therefore, this function does not preserve Cauchiness. Okay, so a continuous function does not preserve Cauchiness. But what about the uniform continuous function? Suppose we have a uniform continuous function. Does it preserve Cauchiness? Yeah, answer is yes. So you can easily show that if a function is uniformly continuous, then it will preserve Cauchiness. So, but let's do it. So let's say we have a function, let xn be Cauchy in x. Okay. And so therefore, for any epsilon greater than 0, I'll just do it informally. For any epsilon greater than 0, there will exist integer k, I mean positive integers, such that m in greater than k will have xn. Okay, so now in place of the epsilon, I will just use delta in this case. So distance between xn comma xm is less than this delta. Delta is this delta I'm talking about. Now, because xn and xm is less than delta, or therefore we can have because f is uniformly continuous, rho of f of xn and f of xm is less than epsilon. Okay, so therefore you can easily, this is just informal way to show that if a function is a uniformly continuous, then if we have a Cauchy sequence xn in x, then f of xn is a Cauchy sequence in y. Okay, so what about the converse? So converse in the sense that suppose we have a function which has the property. So let's say we have a function. Converse means, converse statement, I mean say that suppose we have a function f from x to y, and whenever, so such that it has this following property: whenever xn is Cauchy in x, f of xn is Cauchy in y. Okay, so actually we have an example that we can show that we have such a function which satisfies this property, but it is not a uniformly continuous function. So for example, you can take, I'll just give you one such example. So we'll take x equals to set of all positive integers starting from 1. So 1, 2, 3, 4, all these natural numbers. Union, if we take this set, n plus 1 by n plus 1, such that n equals to natural number, and given with usual distance, usual metric on x, so your real line metric on x. So then if we define the function, which is the characteristic function of n. So I mean, to define a function f from x to 0, 1 by f of n is equals to 1 and otherwise 0. So f of 1, other 1 and f of x equals to 0 otherwise. So you can verify that this is such a function which speeds up Cauchiness. That means you can have a Cauchy sequence in x, then f of xn will be Cauchy in 0, 1. Okay, but this is not a uniformly continuous function. Okay, so this is such an example. So now the question is, we have a function which is continuous, and we also have a function which is uniformly continuous, and in between them there is one more function which speeds up Cauchiness. Okay, so now we want to record that function. So we'll write as a definition, such function as a definition. So let xd and ydo be matrix spaces. We say that f from x to f is said to be Cauchy continuous if it maps Cauchy sequences in x to Cauchy sequences in y. Okay, that is function is also known as in literature Cauchy regular function. Okay, so now obviously I said that the Cauchy continuous function is in between continuity and uniform continuity, but I have not shown that a Cauchy continuous function is a continuous function. Yeah, I will show it. So that means what it means to say that uniform continuous function is Cauchy continuous function, and I will show you that Cauchy continuous function is continuous function. It's something with the internet. Am I audible still now? Is it?
Yes, sir.
Mahalakshmi, am I audible?
Yes, sir.
Hello?
Hello. You are audible. sir.
Yes, sir. You're audible, sir.
Hello?
Yes, sir. You are audible.
Hello?
You are audible, sir.
Okay, okay, fine. I can't hear you, so but let's do it. Okay, so why a Cauchy continuous function is a continuous function? Let's do the proof. So let xn be a sequence in x, and let's say xn is xn be convergent to p in x. We'll show that we are assuming that the f is a Cauchy continuous function. We'll show that f is continuous at p. Okay, so xn be convergent to p. Okay, so now we'll show that because it's convergent to p, we'll show that we will show that f of xn is convergent to f of p. Okay, to do that, we'll construct a new sequence. So consider the sequence x1p like this, x2p, and so on, like then p sequence in x. Okay, so first term of the sequence is x1, second term p, third term again, now I'm taking x2 and then p and so on. Okay, so then you can easily say that then the above sequence, then the above sequence is Cauchy in X. Okay, the above sequence is Cauchy in X, and since F, we assume that F is Cauchy continuous. So since F is Cauchy continuous, since F is Cauchy continuous, so this sequence F of X1, F of P, F of X2, F of P, and so on. This is a Cauchy sequence, is Cauchy. Sorry. Cauchy in Y. Okay, now you can see that this sequence, the Cauchy sequence, and has a convergent subsequence, which is convergent to F of P. You can take the every even terms, the first term, second term, fourth term, fifth term. So if you take every even term of the sequence, F of X1, F of P, F of X2, this is convergent to F of P. So we have a Cauchy sequence and has a convergent subsequence convergent to F of P. Therefore, the sequence, the actual sequence is, that means the sequence F of X1, F of P, F of X2, F of P is also convergent to F of P. Therefore, if we consider the subsequence, which consists of the odd terms, like first term, second term, and then, sorry, first term, third term, fifth term. So that will be the sequence F of Xn itself, which is also going to converge to F of P. Okay, so therefore we proved that if we have a Cauchy continuous function, then it is a continuous function. Okay, so therefore it's actually Cauchy continuity. The concept of Cauchy continuity is in between, like say uniform continuity and continuity. Okay, so now we'll spend a little more time on discussing about Cauchy continuous function and its property. Okay. Okay, by the way, do we have any question before we proceed? Any question? Okay, I think I have problem with the headphone. We'll discuss later. Let me complete. So first theorem, we'll say that suppose this is a theorem. Let A be a non-empty subset of the metric space and Y rho be a complete metric space. If F is a Cauchy continuous function, then F has a Cauchy continuous extension to closure of A. So that's we are trying to prove. So we are saying that if we have a Cauchy continuous function with codomain as a complete metric space, then you can extend that Cauchy continuous function to the closure of A. Okay. So to do that, I will. Okay, white screen. Okay. So we have a function. So A is a proof. A is a subset of X. Okay, and we have a function F from A to Y, and F is Cauchy continuous. So what we have to do, we have to construct a function G, which will be an extension of F, and which is also a Cauchy continuous function. Okay. To do that, let's take a point. Let X belongs to closure of A. So because X belongs to closure A by definition, so then they're exact. A converges to X. Okay. Now, because it's convergent, so A should be Cauchy. So then An is Cauchy, and because An are the elements from A and F is Cauchy continuous on A, so therefore F of An, this sequence is, since Y is complete, okay, since Y is complete, F of An converges to some element of Y. So let's take the element Yx belongs to Y. Okay. We are defining a function. So define G from closure of A to Y by G of X equals to Yx. Okay. So this is the definition of our function. Obviously, we need to check whether G is well defined or not. Okay. Look. So let's check it. Let's say that we have another sequence Bn, which is also convergence to. So let Bn be a sequence convergent to X. Okay. So then we'll consider then again we'll take the splice sequence, the same concept. So then we'll take the sequence A1, B1, A2, B2, A3, B3, and so on. So this is also going to be a Cauchy sequence because you can see that the even terms are convergence to both are converges to X, even or both type of subsequences of this sequence converges to X. So you can clearly see that it is also a convergent to X, and it's not also a Cauchy sequence. Okay, so it's Cauchy sequence. And because AIs are BIs or ANs or BNs are from A, so and if is Cauchy continuous, so therefore be F of B1, F of A2, F of B2, and so on. If you go this way, this is also going to be Cauchy in Y. And if you now F of A1, F of A2, F of A3, so the odd terms or odd subsequence of this sequence is convergent to you already seen that F of An converges one and it has a subsequence which is convergence to Yx. So therefore the sequence itself converges to Yx, and from there we can conclude that F of Bn is also convergence. So consequently we can write sequently F of Bn converges to Yx. So therefore it's okay. This function is well defined. And also now you need to check that it's whether it's an extension of F or not. Okay. So now for any element, so it's a well-defined. First of all, we observe that it's a well-defined function. Then we have to check whether it is an extension of F or not. Okay. So let's take an element A belongs to A. Okay. So then we can consider constant sequence A, which is convergence to A, and therefore by definition, it will be same. It will be Yx. So you can clearly see that it's G of A is nothing but F of A. Okay. So I'm not spending time on that. G of A equals to F of A. Okay. Taking constant sequence. Okay. So it's all right. So now only thing we need to show that that G is a Cauchy continuous function. Okay. So now let's check whether G is a Cauchy continuous function or not. Okay. I have to erase this part. Okay. So let Xn be a Cauchy sequence in closure of A. we have to show that G of Xn is Cauchy in Y. Okay. Now, by construction, you can show that by construction for each n, we can find an in A such that G of Xn comma an is less than 1 by n, and at the same time, rho of f of xn, sorry, not f of xn, f of an, comma, g of xn is also less than 1 by n. Okay. So you can check that, you can actually construct this one. Okay, so I'm not spending time on this construction, but you can do it for each n. You can find a sequence of an in A such that distance between xn and an is less than n, and at the same time, this distance between f of an and g of xn is also less than 1 by n. And since xn is a Cauchy sequence, okay, since xn is Cauchy, it is easy to show that an is Cauchy. And since f is Cauchy continuous on A, since f is Cauchy continuous on A, f of an is Cauchy. Again, by inequality, so thus g of xn is Cauchy. Okay, so therefore we prove that g is also a Cauchy continuous function. Okay, so that is the idea. So if we have a Cauchy continuous function defined on a non-empty set, and obviously codomain is a complete metric space, then we can extend this function to the closure of A, extend in the sense that you will have another Cauchy continuous function, and if you restrict that function on A, you will get the same function back. Okay, so that's the idea. So now let's proceed from there. So this is what this theorem says. Okay. Okay, this is another basic property of continuous function. We know that if we have two continuous function f and g defined on a metric space, then their pointwise product f into g is also a continuous function. Okay, but I think you are familiar with that, that it is not so for uniformly continuous function. That if we have a two uniformly continuous function, their product, if we take the product of two uniformly continuous function, then the product may not be uniformly continuous function. You can try to find an example. Okay, obviously without looking at. So now we'll show that if we have two real valued Cauchy continuous function, then their product is Cauchy continuous. Okay, so it's very simple, but it's similar to the proof for the. Okay, so that's another result. I think you are also familiar. If you take the bounded uniformly continuous function, then the product of two bounded uniformly continuous function is uniformly continuous. So if you do the same approach over here, you can easily deduce this. Okay, you can write the proof of this theorem. Okay, so I'll just tell you what the tricks. I think you are familiar with the trick very much. The idea is that you have to take f of g, like f g of anything like f of x1 or f g of x2, and not this. Sorry. So if we have f of x1 into g of x1 minus f of x2 into g of x2, then you can write f of x1 into g of x1 minus f of x1 into g of x2 plus f of x1 g of x2 minus f of x2 g of x2. Okay, now we use triangle inequality. You will have mod of f of x1 into g of x1 minus g of x2 plus mod of f of x1 into mod of g of x2 minus g. Yeah, I think, sorry, I messed up here. Yeah, it should be g of x2 and f of x1 minus f of x2. Okay, now if we have, you can use this property or idea to prove this. Okay, Cauchy continuous function xn and show that f into g is the Cauchy continuous function. Okay, do not forget that Cauchy continuous function, if a function is a Cauchy sequence, it's a bounded sequence. We have used that trick, that idea. Okay, so I'm leaving it to you. Okay, so it's very simple proof. You have already done this type of proof before. Okay, let's move from here. So now we'll prove this result. So obviously we have proved that that every Cauchy continuous function is continuous. So obviously the natural question is, what is the condition on metric space, or from where we are, what are the types of metric spaces where continuous function are Cauchy continuous? Okay, so this is the theorem we're going to prove. But theorem, I need the notion of Tietze extension theorem. I don't know how many of you know the Tietze extension theorem, but I assume that most of you do. Some of you are not familiar with that. So I will just recall what is the meaning of Tietze extension theorem. Okay. So let's take. It says that if we have a topological space, okay, if it is a normal topological space. In by normal, but yeah, metric space is a normal topological space. Okay, so you can assume that if you have a metric space, the results work. Okay, so this is the result I meant to say. So if you have a metric space, and if we have a closed subset, closed, and suppose can I take a little break? Actually, I have some margin call.
Yes.
If you don't mind. 1 minute break.
Of course, sir. No issues. Yeah, okay.
Yeah, okay, thank you. Okay, let's- Okay, all right. Is it visible?
Yes, sir. Yes, sir.
Madam, is it visible? Hello?
Yes, sir. Your screen
Yes,
is
sir.
visible.
Hello,
Yes, sir.
am I audible?
Yes, sir.
Yes, sir. You're on.
Okay, fine. Okay, so the idea of Tietze's extension theorem is that, so if we have a matrix space, and if we have a non-empty closed, so non-empty closed subset of X, and if we consider a function A from A to, can take R, okay, then you can extend this function to whole of X. Okay, so there is an extension. So there exists an extension G from G from X to R of F. That means G of A equals to F of A for all A belongs to A, and G is also continuous function. Okay, so that is known as Tietze's extension theorem. Okay, so now we'll use this fact to prove our result. Okay, so what is our result? We are saying that if we have so function is continuous, if it is the Cauchy, then we have, okay, let me state that one. So theorem says that, so a matrix space is complete if and only if each continuous function from X to an arbitrary space is Cauchy continuous. Okay. Okay. So I think okay. Well, let's see. Well, let's see. I think it's not, should not be arbitrary space. It should be real. Okay. So first part is very easy. Suppose you assume that it's a complete, then we can easily prove that a continuous function is a Cauchy continuous function. So the idea is that let's take a Cauchy sequence xn in X. Okay, and since D is complete, so xn is convergent to some element A. So now xn become a convergent sequence, and F is continuous. So then F is continuous implies that F of xn is convergent to F of A. Therefore, F of xn is Cauchy. Okay, so therefore F is a Cauchy continuous function. So one part is very easy. If there is a complete matrix space, then continuous function are obviously Cauchy continuous function. The converse part, okay. So we prove the converse one. So suppose that X is not a complete matrix space. Okay. So suppose X is not complete. Not complete means, the complete means every Cauchy sequence is convergent. So not complete means there exists a Cauchy sequence which is not convergent. Okay. So then there exists a Cauchy sequence xn in X which is not convergent. To any point of X. Okay. By the way, because we know that if we have a sequence which is Cauchy and has a convergent subsequence, then the sequence itself is convergent. Okay. So therefore, because the sequence is not convergent, so xn has no cluster point. Okay. So also note that xn has no cluster point. Okay. So because xn has no cluster point, it's said A, which is collection of all xn, n belongs to natural number, is closed in X. Okay. So Now what you can define a continuous function. Okay, so define and close, and not only that, it has no cluster point. That's also important. So f from A to R. So that's why I told you that it's not arbitrary, it should be real value. Okay, so f from A to R, we define a function f of xn equals to n. Okay, so then obviously it's a continuous function. Okay, because it has no cluster point, first of all. It has no cluster point. So therefore, if we consider the relative topology on A, okay, so f is continuous. Then f is continuous on A. Now, what we'll do, we'll use the Tietze extension theorem and extend it to whole of X. Okay, so then by that extension theorem, there exists a continuous function X to R, and is continuous, and G of A equals to f of A for all A belongs to A. And it's obvious that G is not a Cauchy continuous function, because xn is a Cauchy in X, but G of xn, which will be the n, is not Cauchy. Okay, so therefore we have a map which is not Cauchy continuous, but it's a continuous. Okay, so we got a contradiction. So another way to say that, or contrapositive way, whatever. So if X is a if we have such a space where every real value continuous function is Cauchy continuous, the space should be complete. Okay. So this is the proof of the theorem. So it's a very important proof. We can actually characterize a complete metric space in terms of this. Okay. So a metric space is complete if and only if every real value Cauchy continuous function is every real value continuous function is Cauchy continuous function. Now, from this theorem, we can deduce further, and we have this following already. So, in general, the idea is that if we take a continuous function and take the reciprocal of function of that function, so then it's continuous. Obviously, non-vanishing part is there. Okay, so similarly, for a Cauchy continuous function, it is shown. So, if we have a Cauchy continuous function, and then if we take a reciprocation of A, it's Cauchy if and only if this is complete. Okay, so this is what is this an application of the theorem. So one part is very easy. So, for example, if we take is complete. Okay, suppose let this complete, D be complete, and let's take F is Cauchy continuous. So Cauchy continuous. Because it's a Cauchy continuous, it's going to be F is continuous. And we know that then 1 by F is continuous. And because this is complete, and we prove that continuous function Cauchy continuous in that case. So 1 by F is Cauchy continuous. Okay, that's all. The first one part is very easy. The other part, so we are assuming that we have a set. We have a metric space X such that every real value Cauchy continuous, for every real value non-vanishing Cauchy continuous function, the reciprocal of that function is also Cauchy continuous. We need to prove that D is complete. Okay, suppose D is not complete, we'll prove the other way. So we'll prove by contradiction. So the converse part. Suppose XD is not complete. So in this case, let X cap be a completion of X. Okay, just a completion of X. And then we have a point. Okay, so let P belongs to X cap minus X. And obviously such a P exists because it's not complete. Okay, so then define a function. So then define f from x to r by f of x equals to c cap x comma b. Okay, so you can easily show that this function is a Cauchy continuous function. Okay, it's just using triangle inequality, you can easily prove that it's a Cauchy continuous function, but f is Cauchy continuous. But 1 by f is not Cauchy continuous. Okay, so we get a contradiction. Okay, therefore it's complete. So this is a proof of this corollary. Okay, now we have the last theorem that we are going to prove. So again, before I move to that proof or the theorem, okay. So again, let me repeat what we mean by Tietze's extension theorem, because this extension theorem is the important part of the story. It says that again, if we have a matrix space and A is a closed, it's very important, it's closed and non-empty. Then if we have a continuous function from A to R, then it has an extension. Okay, so extension exists of this function. Okay, so now we'll prove that for Cauchy continuous function, this closedness is not needed. Okay, if we have just non-empty subset of X, then any Cauchy continuous function can be extended to whole of X. So this is the last result. Let Xt be a matrix space and A be a non-empty subset. If Cauchy continuous function, then F has a Cauchy continuous extension to whole of X. Okay, so proof is very easy now. We'll just do it one by one. Okay, so F is Cauchy continuous. What we will do, we already proved that initially, if we have a codomain is a complete matrix space, then we can extend it to the closure of it. So first we will extend, let's say f cap, or what this mean? Let's say f cap from closure of A to R. Wait, closure of A has a subspace of x cap D. Okay. So the completion of X. We extend F to the closure of A, but we consider closure of A as a submatrix space, or as a, if you think in terms of topological space, so subtopological space of the X cap D cap. So that's the first idea. So we have this is Cauchy continuous extension, of course. So we already proved that such extension is Cauchy continuous. Okay. Now, because X cap D cap is a closure of A is defined and X cap D cap is complete. So what we can do, we can extend F cap to basically, okay. So we'll do one by one. Not a minute, just a minute. Okay. So it's a Cauchy continuous, therefore continuous. Okay. So plus it will be continuous. So it will imply that F is continuous. And now by Tietze's extension theorem, sorry, F is continuous on CL of A. And by Tietze's extension theorem, so it has an extension to X cap A. So we have a function G, let's say G cap, you can write, which is from X cap to R, and G cap is continuous. Okay, and now because X cap is a complete matrix space, so G cap is Cauchy continuous, because we know that in a complete matrix space, Cauchy continuous functions are continuous functions are Cauchy continuous. So therefore, G cap is Cauchy continuous. And if you restrict now G cap to A, so it's I mean G cap to X is of course going to be the extension of A. Okay. So okay, let me repeat again little bit. So F is Cauchy continuous. So therefore, we can extend it to the closure of A. We consider closure of A as a subspace of X cap D cap. Then because it's a Cauchy continuous, it's a continuous. So because it's a continuous and closure of A is a closed set, by Tietze's extension theorem, we can extend continuous function to a continuous function of X cap. And now X cap is complete and G cap is continuous. So therefore, G cap is Cauchy. Okay. And now G cap is Cauchy on X cap. It's of course going to be Cauchy on X. And G cap is nothing but the extension of it. Okay. This is the proof of this lecture. So that's all, I think. Yeah. Any question from the audience? Okay, what about, I just wanted to ask the audience, what do you think about instead of Cauchy continuous, if we consider the uniformly continuous function? Do you have an extension to whole of X? What do you think? Okay. Hello, am I audible?
Yes, sir.
Hello, hello. Am I audible?
Yes, you are.
Mahalakshmi?
Yes, sir. You are audible.
Hello. Yes, of course we have that. Okay, so someone asked that is there any Cauchy continuous function? Okay, I think I should rejoin. Then we can discuss properly because there is some problem with headphone, I guess.
Sir, you are audible.
I think he left.
Yeah, okay, we can wait.
Okay.
Also, there is one question in YouTube live stream. Okay, thank you, Vinay.
Hello, am I audible?
Yes.
Yes, Tista just captured my attention that she wrote there might be a silly doubt, but I was confused what the space X cap, how is it constructed? Well, I would like to say X cap is the completion of a metric space. So it is constructed by taking all the Cauchy sequences on that space, and this collection is non-empty because we have constant sequences that are Cauchys. So then we define an equivalence relation there. So you can find it in any metric space book. Okay, also Kumarasan sir's book is there, metric space. I think you can find it there. It is completion of a metric space. At every metric
Sujit,
space.
you can discuss now. Argha sir has joined.
Oh, okay, okay, ma'am. Okay, ma'am.
Yeah, yeah.
Definitely, definitely.
Okay, so sir, can you hear us?
Hello, am I audible?
Yeah, sir, you are audible.
Okay, okay. Actually, there was some problem with this. Okay, now, do you have any questions from audience?
Yeah, actually, Sujit wants to say something.
Yeah. Sujit?
Yes, sir. Is there any Cauchy continuous function that are not uniformly continuous?
That we have discussed at the very beginning. So if we consider, shall I set the screen? Then,
Yes, sir.
thank you.
Oh, okay, sir.
Okay, just a minute. Is it visible?
No, not yet, sir. Now
Yeah,
it's
now it's
visible.
Okay. Okay. Yeah, so if you consider X as the set of all natural number, union with this set, like n plus 1 by n plus 1. By natural number, I said, I mean the set like starting with 1, 2, 3, 4. Okay. So n belongs to set of a natural number. And usual topology, if you consider over here, and then consider the function, which is the characteristics function of the set of all natural number n. Okay. So like what we are defining f of xn equals to 1 if x belongs to natural number, 0 otherwise. So this is an example of Cauchy continuous function, but not uniformly continuous function, because you can find that. So the Cauchy functions on x are nothing but those functions which are eventually constant. Okay. So therefore, because that constant, you can easily get that it's Cauchy, f of xn is also Cauchy. But it is not a uniformly continuous, because if we take element like 1 plus something like this distance between n comma n plus 1 by n is 1 by n plus 1, and you can make it very small, but f of n and that, it's 1 and 0. So because of that, it's not uniformly continuous function.
Right, sir. Oh, thank you, sir.
Yeah. Any other? Okay, I ask one question. Anyone from audience? Like, we said that if we have a continuous function defined on a closed set, then we can extend it to whole of x. But for Cauchy continuity, we don't need the closeness. What about uniformly continuous function? If we have uniformly continuous function, can we extend it to whole of x? Okay, think about it later.
Yes, sir. For that, we need a dense subset.
Okay. So he said that if we have a dense subset, then we can
extend. Uniform continuous extension.
Yes, that we can do. Okay. Any question? Mahalakshmi, I think then you have to conclude.
Sure, sir. So, is there any question, right? No more questions, right?
No question in chat box.
Okay. Thank you all for being part of today's talk. A heartfelt thanks to Dr. Argha Ghosh for the insightful presentation. Special thanks to the MTTS Trust and the organizing team for making this event possible. Now it's time to capture this moment. I request everyone to turn their cameras on for a group photo. Jyoti Di, you are taking the photo, right?
Okay, I will do. Okay, so let us some more time. Okay, so on the countdown of 3, we'll click a picture. So 1, 2, 3. Okay, we can wait for some more time. Yeah. Okay, thank you.
Once again, I'd like to thank all of you. Your presence made this event a success, and we look forward to seeing you at our future event. Have a great day. Thank you.
Yeah, thank you, everyone. Bye.
Thank you.